this session is the right one. And hopefully these 4 papers will answer this question. So we start with a paper entitled The Effects of Language Modeling and its Personalization on Touchscreen Typing Performance. The paper will be presented by Andrew Fowler from the Oregon Health and Science University. The co-authors are Partridge, Ciprian, Chelba, Xiaojun B, Tom Ouyang, and Shumin Zhai. This paper received an honorable mention award, so the best 5% received an honorable mention award.
Can everybody hear me? Okay, I'm going to be talking about using language models to make typing better on touchscreens, particularly smartphones. Now, if we think about mobile text entry, obviously smartphones are everywhere now. But if you think about entering text on that phone, even if you're pretty good at it, it's not as fast as a standard keyboard, and there are more errors involved. And that difference between like a standard keyboard and a smartphone contributes somewhat to this effect that a smartphone is more of an information consumption device and a computer is more of an information creation device. And another thing about smartphones is that they're very personal. It's on your person at all times, even more so than perhaps a laptop. So that's an interesting feature of smartphones. For those of you who don't know, a language model is just a way of modeling how words and letters go together. I would venture to guess that every modern smartphone uses a language model, and they're used for a variety of reasons. So for error correction, for auto-completion, and for personalizing the phone to a single individual. The problem is that if you want to say like how much is a language model helping, that's quite difficult to do. One reason for that is that accuracy is hard to measure. You need to have like a lot of data to be able to count how many words went wrong, and it's hard to do that with human subjects. And the other thing that's hard to measure is if you're personalizing the phone, is that helping, and how much is it helping? So you might say, well, smartphones already do this, but it's kind of hard to find a paper about like how much is a language model helping. And it's particularly not a solved problem. There's this site, if you excuse my language, called Damn You Autocorrect, where people have these funny examples like government is back up and ruining, or we are going by taco, where the phone does something silly. By the way, it takes a long time to find PG rated things on that website. So here's what we did. We created an entire evaluation system. And instead of using human subjects, we created a typing simulator that simulates how a person might type with noisy input. Then we built a decoder to kind of take that back to the words themselves. We used a large language model, and we used a smaller personalized model based on that person's words. And then we were able to simulate over many simulated users with real text and get sort of some nice concrete numbers on how much these techniques might be helping. So a little bit of background. Language models have been used for text entry for a long time. Some people still use this T9 system where you have nine keys that represent groups of letters, and then the phone kind of reconstructs what the words might be. Chinese, for instance, it poses an interesting problem for text entry because there's so many characters. A lot of the methods for doing so, you sort of have a Roman phonetic spelling of different words and characters, and then that sort of ambiguously describes what the characters should be, so you need language models for that. And there is at least one paper on correcting errors on a stylus keyboard rather than a touchscreen keyboard. Adaptation similarly has been extensively studied. I won't talk about all these individually, but they're interesting. But looking at adaptation in text entry, papers are very scarce, and there is a nice paper by Tanaka Ishii, which I recommend you read. So, what is language model adaptation? Well, these so-called n-gram models are useful, where you're looking at the previous few letters or few words. But mismatch in domain is a big problem. And what that means is these big models are usually trained on the web or on lots of newspaper text. And if you are evaluating in a different domain, you get big drops in performance. Even, in fact, if you just evaluate on a different newspaper. You might say, well, let's just train on the nice in-domain data. Well, usually there's not enough of that. So you want to be able to leverage this small amount of data and this big, well-trained, well-smoothed data. So why would we do adaptation for text entry? Well, it turns out it's well-suited for that. It's a classic adaptation problem. There's a small amount of in-domain data that's highly individualized. Any sort of performance enhancements you can get are good. And so just in a nutshell, what we did was we used what's called the Enron Corpus, and I'll tell you a little bit more about that in a minute. We take the user's text tied to a specific user, and then we mix that with the background model, which is trained on the web, and we are able to ask, are we going to see improved accuracy when we do this? Is the system going to make fewer word-level errors? So what did we use for our big, giant background model? Well, it's a bigram model, which means it's conditioned on the previous word. It was trained on lots and lots of text from the web. It's smoothed, which means it's in NLP terms, smoothing is when you assign probability to things you've never observed, which turns out to be a good idea. We use a specific type of smoothing called CATS because it's better suited for this next thing, which is pruning. We had to take this model and make it small enough to fit on a phone. And it has a vocabulary of 168,000 words. So what is the Enron Corpus? Some of you may remember the Enron company, which ended up getting in huge trouble. It was an energy trading company, and they basically defrauded many people, and they were some pretty bad guys. It turns out, while they were being sued by many parties, 600,000 of their emails became public knowledge. So from a legal standpoint, this is like a lot to look through. From a data standpoint, it's a bunch of emails that we don't have to worry about privacy, and we also have metadata, which means we know who wrote the emails and who they wrote them to and things like that, what day of the week they wrote them to. And surprisingly, well, maybe not, most of them are really boring energy trader emails. They're not about, like, let's defraud people, although there are some of those. So why is it specifically suited to text entry? For one thing, it's human communication. It's something that a person typed. Secondly, it's written, so as opposed to speech. It may not be something somebody typed with their thumb on a mobile phone, because there weren't many mobile phones. Well, there were, but certainly not as many smartphones in that time. And we have this nice property that we can do personalization experiments because we know who typed each word. So the first thing we had to do was pre-process the Enron corpus. I'm going to totally skip that step, but that just means we kind of cleaned the data to make it look nice. It's actually very hard to do that. And we, I think, published an appendix to the paper that explains how we did that. Then we split it up into two main sets, a development set and a test set. You can see the counts there. And really we wanted them to have sort of the same distribution of, like, there were some users with lots of text and some users with not so much. And I think every user had to have 1,500 words or more. And then we also only used sent messages because that's sort of more tied to that person. We can know for sure that this person typed that. Although even that was a little bit hairy because some of the people had personal assistants who would type emails for them. So what did we do? How did we simulate a user? Well, we say, what if this person was going to type all of their emails? We're going to say one tap at a time how they would do that. So we know from other work that errors in taps, that is the sort of how the tap location varies in two-dimensional space, roughly follows a Gaussian distribution. So what we can do is we can say sample from a distribution, and that'll give us like a point for each tap, some of which might not be on the correct letter, which is good. We want those errors in there. We had certain simplifying assumptions. We wanted to really get to the core of, like, will this work at all? So we took out a lot of the extra bells and whistles. For instance, we made the corpus only A through Z. We made it so the space bar was always correct. It's kind of a weird key on the bottom there. It's kind of harder to model. We didn't have cognitive errors, so like there's no, if there are any typos, we assume that was correct. And we didn't assume that the person would try to go back. They're always typing, they're always aiming for the right key, and they never try to go back. Backspace is actually a very interesting subject, and if you're interested in that, I suggest that you read my dissertation when it is done. So here's an example of 1,000 sampled taps centered on the F key. So you can see some of them are on other keys. It's about 12–13%, and that's based on observations from other experiments. So now that we have all these locations, what we want to do is sort of reconstruct what the text was based on that set of locations. So what we did was we used an algorithm to generate a list of possible words, and then we gave each word a score based on a combination of two factors. The first factor was you got a score for each letter based on how far the tap was from that letter in a sort of Euclidean distance space. And it turns out it's the square of the Euclidean distance because of the way the math works out. But essentially it's, if you have a candidate word and it has a P on the first letter and the first tap was far from the P, that's not going to get a very high score. And secondly, the language model can very quickly tell you what words are likely and unlikely given just the way language is. So the word the is going to be more likely than insert random word here. How about falafel? And then what we do is we combine the two, spatial and language model score, using linear. Actually, I don't think it was linear interpolation. We were in the log space, but that's not terribly important. And then we say, now we're able to arrange that list of possible words into highest scoring on top. We pick the top one, and that's what we go with. Maybe it's wrong. Here's the math for those of you who are interested. Essentially, this B is the score of the word given the context and what you typed. L is the language model score. And then we subtract using this gamma parameter the spatial model score. And we tuned that on that gamma on the dev set, but we did not make it specific to each user. It was sort of performance across all the users. And then we just have to find the best scoring word, and that's what that bottom one means. So we had sort of three main experiments that we did. One was no decoder at all, so you really have to, every tap has to land inside the key. So this is what would happen if you didn't have a language model or a spatial model on your phone. And then there's the basic one that just uses the background model and the spatial decoder. It doesn't try to adapt to the user. And then there's the adapted one where you have a personalized model. And then there were two things we evaluated. One, the most important one, which was really only possible when you do it this way, is word error rate. So and this is the strength of correction. So you just count how many words were wrong. It's pretty easy to do once you have this integrated system. And then a sort of secondary result is the strength of prediction. Language modeling and language modeling can help with predictions too. And here, the metric here is keystroke savings. If you're familiar, if it takes you 8 taps to type a 12-letter word, that would be 25% keystroke savings. And very important point here is when we measured efficiency, we didn't have any spatial noise. We were assuming perfect typing, and then we gave top 3 words at each point. So we assumed that the user would tap their word if it came up in that top 3. And then we just counted how many taps they saved by doing that. Again, this is a secondary result. So the way we did personalization, we kind of have a 1 minus lambda times the adapted model plus lambda times the background model, so you can tune the strengths of the 2 models. It's a really simple unigram model built from just the words in the previous emails by that person. We tried it with a moving window. It turns out that the benefit you get from learning that user's words is best when you just never forget a word that they used. So it's really an infinite moving window. It's just always growing. And then we primed that with 30 days emails. We also tried this thing where you make words that are farther in the past less important. So here are our results. So if you didn't have any model, so that you can find out what happens if you turn off, I think you can turn off autocorrect on your phone. You get a high error rate. It's about 38%. Just doing this basic spatial and language model combination gets you all the way down to 5.7% error rate. So it's a nice big jump there. And this OOV column is out of vocabulary words. And then if you do personalization, so you're learning a little bit about that user's words, it gets you another nice gain in or a nice decrease in the word error rate, and a nice jump down in out of vocabulary words. And the efficiency, we see similar gains. Personalization helps, but it turns out that decaying exponential cache idea didn't really help too much. So we've shown that using this integrated model can give us nice improvements in accuracy and efficiency, although efficiency numbers are kind of iffy because you're assuming a perfect user with perfect typing. Personalization helps even more. And so really, making a large-scale system like this is really the only way to tune parameters. Obviously, you want human subjects in a future trial, but having a big system like this, you can try it on millions of words of text or hundreds of thousands of words of text, which is nice. There's an interesting point about false corrections, which is in the paper. I think I'm running out of time, so I won't mention it here. And there's some other future work we can do. There's more advanced adaptation you can do, and certainly more sophisticated ways of modeling typing. So I just wanted to thank my co-authors and Brian Work, who is my academic advisor.
Metrics, were you using the decoded version, or are you looking at just the top best? So what I mean by that is, so when you are doing personalization and you're going and you're doing word error rate, are you assuming that a perfect context, or are you assuming your decoded context?
Decoded.
Decoded.
So you may have an error that sends the language model off in the wrong direction.
Yeah. Okay. And did you look at count merging instead of just doing simple interpolation? Interpolation?
Briefly, in fact, that was on the future work slide originally. Yeah, that's something you'd like to try. I mean, there's certainly better ways of doing adaptation. We just kind of wanted to see what you could get. Yeah, so that's an interesting point. Yeah, an email is sort of the end result of a typing task, so you don't see anything else that they did. Certainly you can, for instance, if they typed a word incorrectly and then went back, you know that one that they corrected is wrong. That's actually probably more useful in sort of a real-time typing task, where if the system makes a correction and then the person says, no, this is what I wanted, that's a really important piece of information. But I think I'm trying to think of other benefits of knowing the entire typing action. There's certain types of signal, like if you're typing more slowly, then you should probably trust what's being typed more, things like that.